There is a lot of confusion around tensors. Many people have no idea what they are. A lot fewer have kind of heard of them, and then so little people truly understand what they are. And there's a good reason for this. It's buried behind a lot of complex topics like general relativity and quantum mechanics. However, it can kind of be simplified and disguised in a lot of lower level problems, so many people don't even realize what they're using. What I want to do here is help you understand how important they are and how much they are used, not just for the complex topics, but also for simple problems. Now, before I give too much introduction, I should define what a tensor actually is. So a tensor is a mathematical object that doesn't change whenever we have a coordinate system change, but its components are flexible whenever it does change. Does that not make sense already? I'll give you some examples so it'll all become a little clearer. So here we have an object traveling on the xy plane. Has a velocity of 5 meters per second with coordinates 3 and 4. Now let's think about these coordinates a little differently. On my x-axis, I'm going to have 1, 2, 3 unit vectors pointing in my x direction. And I'm going to add to that 1, 2, 3, 4 unit vectors pointing in my y direction. Now what this means is that my velocity of 5 meters is going to have components made up of vectors that are parallel to my axes. Now that's all well and good, but I'm not always going to be looking at it from this perspective. So here we have our perspective changed a little bit. Now instead of looking at it from our normal view here, we shifted our coordinate plane like this, about 90 degrees. So now this is our new vector. So instead of pointing this way, we're pointing this way. And we have new components. So now I'm going to have negative 4x components, or x unit vectors, and then 3 y unit vectors. So that's an example of a tensor. Here, our magnitude of our velocity of 5 meters per second stayed the same no matter how we look at it, because that's not really going to change at all. However, the components, say our coordinates right here and right here, or our unit vectors that add up to make our vector, is going to change. Now that's the core idea of a tensor. But why would I use a tensor here? I can just keep my coordinate system fixed, right? Well, there's not always going to be times where you can keep it fixed. A lot of times our coordinate system is going to be continuously changing. There's not much we can do about it. Here, I'm going to show you another example of where I could use a tensor, where my coordinate system actually does continuously change. Everyone knows the push-up, and there's a bunch of different ways that you could be doing a push-up. There's an incline push-up, a decline push-up, a pike push-up, a handstand push-up, or a push-up where you're on your knees. What if I wanted to find how the weight my arms are taking on changes as I go throughout my push-up? Now you might think that it's not going to change as I go along my push-up, but as we can see, the angle between the floor and my legs is changing, which is going to coincide with the change in the force that my arms are taking on. So if you've already taken AP Physics 1, you'll understand these problems already. But if you haven't, I'll go through it and explain it with you and how it connects to the push-up. So as you can see, we have a block on a ramp at a certain angle here. Now what we want to find is this acceleration as we go down. But we can't just say our acceleration is gravity, right? We can't just say it's g because we're on an angle. And as we can see, our coordinate system got shifted slightly. If you remember my earlier example, we want to try and represent our force as the sum of forces that are parallel to our axes here. Now, as you'll see, if I went even further up on my angle here, that is going to change my unit vectors here. And that's going to change how much gravity is actually going parallel to my ramp and how much is perpendicular to it. So the angle of my ramp is going to change. Now in turn, this is also going to change how much force is being put on my arms as my angle changes throughout the push-up. So now let's look kind of like what we did with the ramp problem at different points in our push-up. Here I have the start of my push-up and I have the end. So what's the difference here? At a normal push-up, I'm just at a flat 180 degrees right here, and my force of gravity is still parallel with my axes right here. Now I can take this to roughly mean that the force is being split evenly between my arms and my feet. But it's going to be different for my end right here. We have our force of gravity, but it's still pointing down the same way. And it's no longer parallel now, is it? So what we need to do, I need to split it up to force of gravity in my x direction and a force of gravity in my y direction. Now this force of gravity in my y direction is still kind of going to be evenly split between my feet and my arms. But the force of gravity in my x direction, that's going to be going solely to my arms. Now this is going to change depending on my angle right here. See, as we go further down, this is increasing. Because at the start, with no angle, that didn't change. But with a greater angle, it does change right here. What if I actually wanted, knowing my force of gravity, what if I wanted to predict, depending on the angle of my push-up, how much my arms are actually taking on? Well, let me show you with a rotation matrix. So to try and predict how much load my arms are going to be taking on, I can use this vector representing my force of gravity right here at normal circumstances, and then I can rotate it using this rotation matrix. Let's look at the vector first. So in our x direction, we have 0 newtons because normally there's nothing going this way. It's just all going down. And then this is roughly the weight of my body in newtons right here. It's my weight in kilograms times 9.8 meters per second squared. Now let's look at this thing right here. I'm making a function right here called my weight of theta. So this is the vector of my weight in terms of theta. So what's happening here? This matrix right here is going to rotate my vector depending on the value of theta in here. So say it's pointing down and then I want it to instead go -30. It's going to be pointing this way instead. Now that is a good way to think about it, but there's a better way to think about it. Now, normally this is our coordinate plane, right? And I have my f of g just going down like this. But if I want to go negative, instead, I can actually rotate my whole entire coordinate plane right here. And keep my force of gravity facing the same way. Now this is kind of what we already saw earlier. Whenever we looked at our coordinate plane at the start and end of our push-up, that's kind of what we're doing. It's the same thing we're doing here, except we can find the actual value of our vector here. So now I've plugged in the values at the start of my push-up and at the end of my push-up. So I approximated at roughly 15 degrees and at the start 0 degrees. So as we can see, at the start, it's unchanged. 0 degrees, it doesn't change my vector at all. And that makes sense because if I plugged in 0 into here, this turns into 1, 0, 0, 1. And if you've taken linear algebra before or watched a couple 3 blue, 1 brown videos, this is the identity matrix. So identity will hold, nothing changes. But let's look at this one right here. When I plug in 15 here, and I multiply these matrices together, I get approximate, it's not the exact value, but I get 190 newtons and -708 newtons. So that means 190 newtons, that's going to be my F of G x. That's going to be my force of gravity pointing in the x direction. Now this is going to be my F of G in the y direction. Remember, that's approximately being distributed evenly between my arms and my feet. So that's going to be one way we can predict my F of G of x, or the weight that my arms are taking on. We can see how my vector magnitude doesn't actually change at all here. If I found the magnitude of this vector again, it's going to be equal to this one still. However, these coordinate changes here do change based on our angle and are going to help me predict this. And as we can see, this is kind of representative of a tensor here. So tensors are often thought of as matrices, but they can be multi-dimensional if you need. And as you can see, our magnitude never changed here, but the coordinates did stay flexible as my angle changed here. Now, you might be saying, why don't I just multiply my force of gravity times sine of theta if I did want to find how much is going in that direction? And you absolutely could be doing that. But this is just one example of one way you could use a tensor. Let's go to an actual needed, super important example of a tensor. One place where tensors are an absolute necessity is in the theory of general relativity discovered by Einstein, which discovers how space-time is warped by large objects in space, and discovered by this equation right here, which features tensors heavily. Before I get to this equation, let me describe to you how it works so you get the gist. So, in the theory of relativity, it describes how heavy objects shift our space-time. In this theory, space and time are brought together as one four-dimensional manifold, simplified right here on this piece of saran wrap. So, in a vacuum, like shown here, with nothing affecting it, everything works as normal. However, if I have a heavy planet, like shown right here, it's going to bend our space-time. So what does this mean? Well, this bending of space-time is kind of representing our gravity. So this means that gravity is going to change how space and time works. Additionally, when we experience this warping right here, our coordinate system is going to slightly change. So why is that? Well, we can think of the saran wrap as having lines across it both ways, like how a coordinate plane would. See, whenever we bend it like this, our lines are also going to be bent, and the angles between them are going to change. So this is going to shift our coordinate system, and it's going to give us new properties in regards to our space and time. Since this saran wrap is like our space-time, a heavy object like this, bending our space-time here, is going to change how the passage of time works, as well as warping our space. So if I'm on an even larger planet like this, rather than a vacuum here, our time is going to move a lot slower. We can think about it like this. This one right here is going to have a larger indent, as opposed to over here with nothing on it. So if I wanted to move a distance like here from point A to point B, it's just going to be a straight line in a sense. However, if I wanted to go that same distance, I have to go through this bending as well, meaning it's going to take me more time essentially to get there, which basically means time is going to be moving a lot slower here. But I've been talking about tensors this entire time, so let me stop rambling and talk about how it's used in the equation. Now, I hope my explanation has kind of made you think a little bit about how a tensor could come up here, about what is changing in our coordinate system and what is staying the same. Well, as we saw, the bending of our space-time could be seen as a coordinate system change. But what is staying the same throughout it? Well, let's look at a tensor that is front and center in the equation, the metric tensor. So here we have the metric tensor. The metric tensor in this equation is an object that contains the distances and angles between axes in our space-time. See, whenever we have a warping of our spacetime, we may see changes in our coordinate system like this, where the angles and distances of our axes may change. Now, inside our actual metric tensor, it contains information about the distances, angles of our axes, and the different local geometry that may show up, but mainly it's representing the gravitational potential energy. Metric tensors aren't only used for general relativity though. If I have two maps like this with different kinds of coordinate systems, say the Gall-Peters map and the Mercator projection, and I wanted to try and find the distances between them, I would need a metric tensor to convert between them because of the differences in angles and the sizes in our coordinate system. So the metric tensor isn't just only used for general relativity here. It is serving a very similar function as these do with each other. So as we already saw, a tensor can be described as a 2x2 matrix with data points inside of them. It can be more than 2 dimensions, but we don't necessarily need that here. So what are the data points inside our tensor telling us? Well, it's describing the distances of our axes and the angles between each other and how that's being warped in our space-time. So here we have an example of the Schwarzschild metric, and this is being used for an uncharged, non-rotating black hole. So why would I ever use this? Say I'm at that black hole and I want to try and give information back to Earth. I wouldn't be able to just take that same information on Earth. It's like if I wanted to use a distance from our previous map and then put it on the other map the same exact way. Wouldn't really work. The distances of our axes and the angles between them have changed a lot, so that wouldn't be very accurate. What we need is our metric tensor to be able to convert between them and tell us how it's being changed. So as we can see, tensors are an incredibly important part of general relativity, which is an incredibly important theory for describing our universe. Because of its invariant nature, we can rely on it to not change too much between coordinate systems. But because of its flexibility in its components, it can tell us a lot of information whenever these coordinate systems do happen to change. Because of these properties, it's incredibly important for concepts like machine learning, electromagnetism, or even material science. Tensors are incredibly important, but not many people even know about them. And I say this because a lot of people wonder, when am I ever going to use these higher level math concepts in real life? And more people wonder, what's the point of doing pure mathematics if there's no use case right now? Well, one of the ways to describe a tensor, a matrix, started out as pure math and study of linear algebra. Hermann Grassmann invented linear algebra and died without seeing any support for it, or even seeing any of the major use cases that linear algebra is used for today. And I think that really sucks. People often condemn these mathematicians for not seeing any use case in their work, but we don't know if years down the line it will be used. We need to let go of the notion that math has to be useful right now, because we just don't know all the use cases yet. We don't know all the problems that we'll have to solve in the world. So next time you're researching some math, you're trying to learn something new, and you think, what are any of the use cases for it? Research it first. And if you don't find anything yet, don't overlook this math, because one day it could be used in the theory of describing our very universe.